working on calculation of pHs of salts. So first problem, calculate the pH of a 0.25 molar CH3COONA, which is actually sodium acetate. So sodium acetate is the salt of acetic acid, so that is why the Ka of acetic acid is given to us. Again, that is 1.8 times 10 to the negative 5. Okay, so which means that our conjugate base here is the CH3COO minus, which is from the acid. Okay, so which means that if this is the base in the solution, remember we are calculating the pH of a salt, okay, not of an acid anymore. So if you're talking about salts, then this is the base in the solution. Okay, why is this the base in the solution? Because CH3COOH is a weak acid. Weak acids give the salts, give basic salts. Okay, and that's why we know that this is a base in the solution. So if this is base in the solution, then hydroxide ions will be in the solution. Okay, and that is what is important over here, because if hydroxides are in the solution, then you have to use Kb, not Ka. Alright, because Ka is for acids, Kb is for bases. Okay, so which means that you need to calculate Kb, which Kb is equal to 1 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5, and this is equal to 5.6 times 10 to the negative 10. Alright, so this is a side calculation that you will have to do in order to calculate Kb. And remember, you calculated Kb because, yes, because this is a base. Okay, this is a basic salt, so you have to calculate Kb for this. Now remember, this might happen in a lot of problems. Alright, so let's set up our equilibrium. CH3COO minus plus H2O. Since this is the base we are concerned about, I'm writing only the acetate. The sodium doesn't really matter. It's a spectator ion. It's not going to have any effect. So then you form the acid and then, of course, the hydroxide ion. Okay, and that's why I really insist that you write the equation so you get a practice of learning how to write the products also. So initial concentration of this one is 0.25. You see, the calculation is not that hard. Getting to set up the problem sometimes, okay, is really where you might falter. So the change then is minus X for the starting material and plus X for the product. So then equilibrium, you have 0.25 minus X as the concentration and X as your concentrations here. So then Kb is equal to 5.6 times 10 to the negative 10. And that's equal to the X squared divided by 0.25 minus X. Okay, and what do you think? We're going to ignore our X? Oh yeah, okay, because the Kb is 10 to the negative 10. 10 to the negative 10, whoa, okay, so ignore the X over here. So which means that this is equal to X squared over 0.25. Okay, so which means that X squared is equal to 0.25 times 5.6 times 10 to the negative 10, and if I were to go ahead and do the square root, and once you take the square root of all of this, X should turn out to be 1.2 times 10 to the negative 5. Now remember what X is. X here is equal to the hydroxide ion concentration. The calculation is asking you for, the problem is asking you for pH. Alright, so this is hydroxide ion concentration. So now you need to find the negative log of 1.2 times 10 to the negative 5, which is 4.92, and this is equal to pOH. So last thing, pH is equal to 14 minus 4.92, and that is 9.08. That is our final answer. How do you know that's going to be the right answer? Well, we're working with a conjugate base. So if you're working with conjugate base, your pH has to be higher than 7. Okay, that's how you know you're on the right track. If you're working with a basic salt and your pH comes out to be less than 7, then you're on the wrong track. You missed something. All right. So that's how you can do a quick cross check of your answer to make sure you're on the right track. Next question, calculate the pH of a 0.052 molar NH4Cl ammonium chloride solution, and the Kb is given to us. Okay, so again, NH4 plus is a weak acid. So if this is a weak acid, solution is going to have hydronium ion concentration. Okay, and so that means we need Ka, not Kb. So we are given Kb. So again, our side calculation here real quick is going to be then calculation of Ka, which is 1.0 times 10 to the negative 14 divided by the 1.8 times 10 to the negative 5, which is that Kb of ammonia, and then this one gives us 5.6 times 10 to the negative 10. Yeah, it's the same as the one that we just did, but anyhow, you still, if you're working on an exam, you still have to do this. All right, so then we can go ahead and set up our equation, which again, you start with the conjugate acid, okay, not with ammonium chloride. You could, but chloride here is the spectator ion, okay, and so NH4 plus. Where is the chloride coming from? The chloride is coming from HCl, okay, that's how you figure out the acidic and basic salts. All right, so you don't have to write the salt of a strong acid or base, plus H2O to give us H3O plus, and then of course the Cl minus, or NH3 there, NH3. So this is what we're calculating for, okay, because this is an acidic salt. So in an acidic salt is going to react with water to give you an acid, okay. Initial concentration 0.052, 0 and 0 for the products. The change is going to be minus X and then plus X and plus X. The equilibrium concentrations are 0.052 minus X and then of course X and X. So then Ka is equal to 5.6 times 10 to the negative 10 is equal to X square over 0.052 minus X, and of course we can happily ignore this one, no problems there. So X square over 0.052, okay, and so then our X square is equal to 5.6 times 10 to the negative 10 times 0.052. Take the square root of everything, and so then X is equal to 5.4 times 10 to the negative 6. Okay, molarity. Now this is the hydronium ion concentration, which we are in luck because we're asked to calculate the pH, and pH is of hydronium ion. So negative log of 5.4 times 10 to the negative 6 molar is equal to 5.27, and you could see again that since you're working with an acidic salt, our pH is lower than 7, okay, versus when we were working with the pH of a weak base, okay, or the salt of weak base. All right.